All right. So we finally have enough information, enough tools to go through RSA cryptography. And this is the kind of the thing we've been building up to in this chapter on algorithms with numbers. So the problem is that Alice wants to send Bob a message. Let's say that message is a binary number X. But there's someone in the middle, we'll call them Eve, who can intercept the message. And we want to encrypt the message so that Eve can't do anything with the information she receives. So the idea of cryptography is that Alice encodes X using some encoding function E and sends the result of that function, E of X, across to Bob. Bob then decodes it using his decoding function. So D operates on the message he receives, E of X, and it returns back X. The picture for this is that we have Alice over here, who has the message X. That message goes into the encoder, which is E. Out of it comes the message E of X, which gets intercepted by Eve. On the other side of this communication channel, so this big long arrow is the communication channel, that's like the internet or something. There's a decoder. That Bob has. Bob decodes the message and recovers X as his decoding function, D acting on the message he received, which is E of X. Now, the whole thing in the whole challenge in cryptography is to come up with these functions E and D. And of course, the function D has to be essentially the inverse of E, right? It undoes what E did. And so there has to be some agreement between Alice, the sender, and Bob, the receiver, in order to have this encoding decoding pair. So in private key schemes, which is one of the main cryptography methods, Alice and Bob meet beforehand to choose the decoder D. An example of this is AES, the Advanced Encryption Standard. In a public scheme, no prior meeting is needed. So somehow they're able to just agree on the encoding and decoding functions over a public communication channel that Eve could be eavesdropping on. In practice, what happens is that a public key scheme like RSA is used to exchange private keys, at which point the faster communication method of AES is used for subsequent communication. So there's essentially this initial handshake. Let's say you and an encrypted website that you're using, your banking site or something. If you look, it'll do private key exchange via RSA, and then it does AES as a private key scheme. We won't go over private key schemes at all, but the public cryptography, RSA, combines basically everything we've seen so far in this algorithms with numbers. So each person has two keys, a public key, which is known to the world, and a private key, which is known only to that person, only to the holder. If you've ever set up your GitHub account, for example, you have to do exactly this. You create a public-private key pair, you put the public key on GitHub, and you keep the private key on your own computer. So when Alice wants to send Bob a message, she does the following. She looks up Bob's public key and encodes the message. And then Bob decodes the message that got sent to him with his own private key. So the idea, right, if you want to send me something, I have a public and a private key. You grab my public key because my private key corresponds to it, and it's the way I'm going to decode. So you basically, you look up my encoder in some sense, You encode your message, send it to me, and then since I have the decoder, the private key, I can decode the message. So as I mentioned, this idea is kind of like we have a function E, and then we have another function. When I have D acting on E, it returns back the original argument X. And so that's like an inverse. And so let's just do a bit of a review here. If we have some function, F, that maps from, I've got one extra bracket here, that maps from the integers 0 to m back onto that same set of integers from 0 to m, we say it's invertible if for every y in 0 to m, there is a corresponding x such that f of x equals y. Right, so it's basically, I have a picture like this. I have the domain and the range, and the function f acts on it, right? And if I pick any x here, there's a corresponding, on the other side, there's f of x, which is equal y. And basically, if I pick any point y over here, there's a corresponding x such that f of x maps that point to this point. Okay. I guess I should have drawn that down here in this space. Okay. So we kind of already know what it means for function to be invertible, but that is what we're looking for. And then there's this nice property, which is long, and it'll take us a little bit to to extract the meaning from it. But what it says is the following: pick two prime numbers, P and Q, and let n be their product. So n is a composite number, which is the product of P and Q. Then find an E that's relatively prime to P minus 1 times Q minus 1. So remember, relatively prime means that the greatest common divisor of E and P minus 1 times Q minus 1 is 1. Right? They don't have any common divisor other than 1. If you can find this N and E, then the mapping where I take X and I compute the X to the power of E mod N is invertible. So this mapping, oops, sorry, just resize that. This mapping here is invertible. And the inverse is given by the following. So the inverse mapping is I let D be the multiplicative inverse of E mod P minus 1 times Q minus 1. And then I decode the message as the message I received to the power of D mod N. And that returns back X. So you can see we're using a bunch of the language that we developed so far, right? The idea of relatively prime, the idea of multiplicative inverse. You can see GCD. You can see modular exponentiation, generating primes, right? Which we also covered. So let me go through an example just to show you what this means. I mean, it's just a numerical example, but then we'll go and we'll get some insight into what's happening after that. So let's pick two primes, 17 and 23, and then n is their product, which is 391. So step 1 was to compute n, which is 391. Step 2 is to compute P minus 1 times Q minus 1, right? Which is equal to 16 times 22, which is 352. That's an even number. So the next thing is that I have to find an E that's relatively prime to 352. I'm just going to take E is 3. Pick E equals 3. Which is relatively prime or coprime to 352, right? They don't have any common divisor because 3 doesn't go into 352. Okay, next step. Is I have to find the decoding exponent, D. So find D such that, what did it say? D should be the multiplicative inverse of E mod P minus 1 times Q minus 1. So that means D times E mod 352 should equal 1. We can find this by calling extended Euclid, right? So call extended Euclid on 352 and 3, and we get that D is equal to, I get 235. Okay, so we've got D is 235, we have E is 3, we have N is 391. And now, and just I can say, can check this, that this actually is a multiplicative inverse by seeing that 235 times 3 mod 352 is equal to 705 mod 352, which is equal to 1. Right, because 352 times 2 is 704, so it goes in twice with a remainder of 1. Now, let's say we want to send a message. I'll just write the message in decimal, so 73. Then we encode as x to the power of E mod n, which is 73 cubed mod 391, and that equals 363. And then we decode using D, and we get x to the power of E all to the power of D, right? X to the power of E all to the power of D mod n. Is equal to, well, it's going to be 363 to the power of 235 mod 391, which does indeed return 73. So we encode here and we decode here. So that's how this works. Now, it all seems kind of magical, I think, right? Like, why is this working? Why? The first thing is that this mapping is invertible, and the second thing is that this is the inverse. if we can show that if we show that this is the inverse of this mapping, then we've also shown it's invertible because we found its inverse. So for the proof of this, I'm basically going to prove that this is indeed this equation here is indeed satisfied, which then tells us that this mapping is invertible and the inverse is just given by raising it to the power of d mod n. Okay. So let's try it out. So we have the following. So we're going to prove, as I said, the second part. Which implies the first, right? Just to show again, we're going to prove that this is the inverse. We're going to prove the equation in green. So we need to prove that x to the power of e, all to the power of d, is equivalent to x mod n. Remember what that means? That's the same as saying x to the power of ed. I mean, x to the power of e to the power of d is just x to the power of e times d, minus x is divisible by n. Now, what do we know? So we want to show this. What do we know? Well, we know something about E times D, right? In particular, we know that D is the multiplicative inverse of E mod P minus 1 times Q minus 1. So let's apply what we know, right? That's really the only thing we've got. So we know that by the definition of D, that E times D is equivalent to 1 mod P minus 1 times Q minus 1. And so what that means is that E times D can be written as 1 plus an integer multiple of P minus 1 times Q minus 1. Right? It means that P minus 1 times Q minus 1 goes into ED an integer number of times, or like some number of times, with a remainder of 1. That's what this expression is saying. So we can write ED as 1 plus some k times P minus 1 times Q minus 1 for some integer. Okay. So then what we need to show, plug that back in to this equation up here. We need to show that x to the power of ed, which is 1 plus k times P minus 1 times Q minus 1, minus x is divisible by n. Okay. Now, what do we do here? This actually looks a little bit like something we've seen. So let me try and remind you or jog your memory. So I guess, first of all, what do we know about this equation? X is a message, so it could be anything. We know that n is a product of primes, and we know that P and Q are those primes, right? So P and Q are primes. But if you remember from Fermat's little theorem, the result looked something like this. It looked like an x to the, or like it looked like a to the power of p minus 1, where p was a prime number, or a to the power of n minus 1, where n was a prime number. So this is actually looking kind of in a similar form. And let me like tease that out so it looks a little bit more similar. So we know since p and q are primes, they satisfy Fermat's little theorem, which then means, by the statement of the theorem, for every a to the power of p minus 1 is equivalent to 1 mod p, and a to the power of q minus 1 is equivalent to 1 mod q. This first one is the same as saying a to the power of p minus 1 minus 1 is divisible by p. And the second one is like saying a to the power of q minus 1 all minus 1 is divisible by q. Okay, so can I now use this to argue something about this expression here? Right, this is the thing we're trying to show. Well, first let me rewrite this expression here. So I'm going to write it as we have x to the power of 1 plus k times p minus 1 times q minus 1 minus x. That's the same, just factor out 1x, and it's x to the power of k p minus 1 times q minus 1 minus 1. And so really, I just need to show that this part is divisible by n, right? Because then, I mean, this is just a number out in front. So if this is divisible by n, then the whole number is divisible by n, rather than going in some, I don't know, some constant c number of times it goes in now x times c times. So I want to show this is divisible by n. So let's first write as x times a to the power of p minus 1 minus 1, where I've just defined a to be equal to, right? This is, I'm going to group together x to the power of k times q minus 1 and call that a. X to the power of k times q minus 1. And then you can see this whole expression is just a to the power of p minus 1. So maybe I will call this thing star. So first write star as this. So that's just the same expression. And now I see that this thing must be divisible by p, right? Because it says it right here. So therefore, star is divisible by p. And then next, I can do the same trick for Q. Next, write star as x to the power of, I don't know, some different a to the q minus 1, where now this a is x to the power of k times p minus 1. And then from this, applying this second line, right? I hope you see what I'm doing here, right? If I just expand out a bar to the power of q minus 1, I recover exactly this term right here. So now I see that star is divisible by q. But p and q are both primes. So that means that it must be divisible by their product, right? Because we know we can always factor any number, we can factor into its, or we can, factor it into its prime factors. And the product of those prime factors is the number itself. So therefore, star by both P and Q. Since P and Q are prime, star must be divisible by n, which equals P times Q. And that then proves the result, right? What we wanted to show was x to the power of ed minus x is divisible by n. So therefore, x to the power of ed minus x is divisible by n. And so we get that x to the power of e all to the power of d has to be equivalent to x mod n. Okay. So that actually proves this result. So now how do we use it, right? What do we do? I think I already went over it, but let me just repeat it one more time. So Bob chooses a public key. That public key is a large number n, which is the product of two primes, and an exponent e, and also chooses a secret key d. So Bob chooses a public key NE and a secret key D. To get the public key, we pick two large n-bit prime numbers, P and Q. The public key is NE, where n is P times Q, and E is relatively prime to P minus 1 times Q minus 1. E could just be picked as 3 or can be picked as something more complicated. The secret key D is the multiplicative inverse of E mod P minus 1 times Q minus 1. And we compute that with extended Euclid. Now, when Alice wishes to send a message X to Bob, she looks up the public key NE and sends the message X to the power of E mod N. We compute that with our mod X algorithm, right? And then Bob decodes the message using Y to the power of D mod N, receives the message Y, computes Y to the D mod N using mod X, and recovers the message. So now if we think about, there are tricks to implement this faster that we're not going over, but basically you can now implement RSA. Like you have all the tools to do it. Your algorithms aren't maybe the state of the art, the fastest ones. There are better ones available, but we now know all the ideas. So the question is, how secure is it, right? Because we actually rely on this all the time. And it relies on the following assumption, which is that think about what Eve has access to. N and E are public, so Eve has access to them, and she can also intercept the message Y potentially. So the idea is that given N, E, you have the public pair, and Y, which has been computed as x to the power of E mod N for some X, but you don't know X, right? You know the E and you know the N that were used. And so given these, it is computationally intractable to determine X. And so there's no formal proof that this is true. But if we just think of how could Eve possibly do it, the only ways I can think of are one, the first one's not a good idea. Eve could try to guess X. If she had a guess, she has access to E and N, so can compute Y and compare it with the intercepted Y, and then determine if she guessed the right X. But as long as we send like fairly long messages, like let's say we send 2000-bit messages, then the number of possible guesses is enormous, right? It's exponential in the length of X. So then check if X to the power of E is equivalent to Y mod N. If X is 1,000 bits, let's say, 2 to the 1,000 guesses. So that is not great. And the other option is she would have to try and figure out D, the decoding exponent. But to compute the decoding exponent, you need to compute the multiplicative inverse of E mod P minus 1 times Q minus 1. And all you have, you don't know P and Q, right? You only know N. So how would you get P and Q? You'd have to factor N. So you could try and factor N to extract P and Q, and then compute the decoding exponent, D. But we do not know an efficient algorithm for factoring. And so as long as we make the message fairly long and make N quite big and P and Q quite large, we don't have any way to solve this. So we believe factoring is hard. And commonly now, we use 2000-bit keys. And so the size of these computations is very large. I mean, the factoring N is just not possible. And similarly, guessing X is just not possible. So as a very last thing, let me just show you a website. I'm going to show you our campus website right now. And if we go to this connection is secure message at the top, we can see the certificate. I hope this shows up for you. And let's go to the details of the certificate. And we see that the signature algorithm is done with RSA encryption in this case. And the public key is RSA encryption, 2000 bit. And so this is, I mean, I'm not cherry picking this. Basically, every site you go to, if you go and you look at what's the public key, it's done via RSA encryption. So this is really like the basis of secure communication. And we've basically learned all the algorithms needed to implement a version of this. So that's all we've done, or that's all we've got for this. In the next lecture, we're going to start with divide and conquer algorithms. And so I hope you enjoyed the lecture, and I'll see you in the next one. Okay, bye.